Fix a point in the plane and consider all paths that go through that point, non-constant path. Then the modulus of that family is 0. We have seen a proof of this, but not explicitly. Remember the function which was 0 everywhere other than in the origin where it was equal to 1. We did show that this function actually belongs to n12 of the plane plus its Newtonian norm n12 is actually equal to 0. In order to prove this, we need to find first of all upper gradient of u and also one that has norm as close to 0 as possible. So we need to find for every epsilon positive a Borel function rho that is upper gradient, and this is less than epsilon to confirm the second claim here. And we did do that by giving explicit constructions for the function rho. Go back to that video and check. I'll make sure I add it to the description. The reason this is proving that modulus of this family is 0 is that if rho is an upper gradient, by following the definitions, integrating rho along any of these paths that hit the origin has to give us at least 1 by definition of upper gradient. So for every gamma from the family of paths going through the origin, this integral is at least 1, which means that rho is admissible for calculation of modulus, and the modulus is infimum of L2 energies. We're talking about modulus 2 to be precise. And that's why we have already seen one proof of the claim that the modulus of path through just one point is 0. In this video, I want to give you a different proof of this fact, which uses the idea that the modulus of annuli in the plane depends only on the ratio. So this is the precise calculation of the modulus of path that join the outer circle of an annulus to the inner one. So consider all the path in the plane which join this to that. You can also go outside and come back. That family has modulus precisely equal to this 2 pi over log of r over r. In particular, we see that this depends only on the ratio and not on the size. In other words, if you have a different annulus at very smaller scale, but the ratio is still the same, you get the same modulus. The precise statement, which is even stronger, can be as follows. So suppose all we know is that there exists some alpha bigger than 1, and there exists some m positive such that for every r positive, modulus of path joining the circle centered at z naught of radius alpha r to circle centered at z naught radius r is less than or equal to m. The reason I'm stating it this way rather than using this precise one is that actually we can here replace this mod 2 with mod p if it's applicable. Or even there is this notion of transboundary modulus. So you can imagine that this is any other type of modulus. And the reason I'm giving you this proof of the above fact is that the method is kind of applicable in many different contexts. So all we need is that for annuli of ratio alpha, the modulus is uniformly bounded, independent of the size of annulus. Then this alone implies that the modulus, whatever modulus this one is, so if this is P modulus, this is P. If this is transboundary modulus, this is transboundary modulus. So the modulus of all path through Z naught is 0. So Z naught is just one fixed point, irrelevant. So how do we begin with annuli and end up with this? Is the whole reason I'm giving you this proof. So Z naught, suppose, is in the middle, in the center of all of these concentric circles. And despite my picture may not seem that way, suppose that for each of these annuli, so this is annulus 1, this is annulus 2, and annulus 3, so on, that, so take a decreasing infinite sequence of disjoint annuli AI of ratio alpha. So each one has the same ratio alpha. Of course, you can find the infinite sequence. You just the next R you pick is, say, half of the smaller circle of the previous one, and then this, of course, never hits 0, and you can go on forever. So you have the sequence of annuli shrinking down to Z naught. Now I want to find an admissible function for path hitting the origin. So some path may start from far out, some path may start very close to Z naught, which are actually the more difficult path to satisfy. So what we know is that if we let gamma I be path joining boundaries of one of these annuli AI, so for each I, let gamma I represent the path joining here to here. So this is in A1. So we know that this modulus is less than m. Since modulus of gamma I is less than or equal to m, this means there exists admissible function rho I for this gamma I. In other words, integrating gamma rho I over gamma is at least 1 for every gamma of the family gamma I. And, well, the integral is pretty close to the infimum. So mod is infimum, so integral of rho I to the power 2 in our case, mod 2, over all of the region, all of the plane is less than or equal to m, say, plus 1. It's easy to see that you don't need to actually to assign any weight, any rho I outside the annulus, because if a curve does go out and come back, you don't need to pick up any integral over the part that leaves the annulus, because this subpath will give us the necessary enough integral to get bigger than 1. So we can only integrate over AI. And without loss of generality, we can assume that support of rho I is inside AI, the closed annulus. So for every I, we have found the one function rho I with this property. Now I want to find an admissible function for the path going through the origin Z naught. And again, the problem is some path start very close to that. So for reasons that will be clear very soon, let's pick us some natural number and let this rho be summation 1 over I going from n all the way to infinity of rho I. So this rho is Borel, because each rho I is Borel. And we claim that this is actually admissible for, so rho admissible for collection of all path through Z0, non-constant path through Z0. Okay, proof of this claim, we see that by simply continuity and intermediate value property of continuous functions, that there exists some, okay, so let gamma be a non-constant path through Z0. It starts somewhere away from Z0, and then it could get away from origin, rotate, do a lot of things, but ultimately at some point it goes through Z0. From intermediate value property, we see that gamma crosses in the understandable sense that, well, it joins boundary to boundary of infinitely many annuli. So crosses infinitely many, well, I want to say more than just that. It crosses all annuli for annuli AI after some I bigger than some number, well, I gamma. So it depends on gamma, this index, but every curve you pick will cross over infinitely many of these annuli after some threshold. Thus, integrating rho, this rho that we defined as summation, integrating rho over gamma ds will be bigger than, and the annuli are disjoint and rho i's are supported on the annuli, so everything works perfectly, so that this will be I beginning from I gamma all the way to infinity of integrating rho I over I ds over the subpath of gamma. You don't have to pass the subpath because, well, rho I is supported only on AI anyway, but each one of these integrals is at least 1, so this becomes summation of 1 over I going from I gamma all the way to infinity, and that's always infinite with equals infinity, which is always bigger than 1. Let's write this out. So this will always be infinite because it's divergent sequence and it's always bigger than 1. So I have an admissible function for this path family. To compute, of course, modulus or estimate modulus from above, we take the L2 energy of our admissible function C. Again, from the disjointness of supports of rho I, this will be less than integrating, okay, integrating over, so my rho definition starts at n, which explains the reason why I start not at 1 but at some n. And then this will be integral over ai of rho I to the power 2, I to the power 2. This is very important here that the supports were disjoint so that this identity actually holds. This not even inequality, it's just identity against area integral. But look, we have chosen rho I so that the L2 integral is less than m plus 1. So this will be m plus 1 over I to the power 2, and then summation happens from n all the way to infinity. So this estimates the modulus from above, but given epsilon positive, we can choose. So for every n, we have this situation. So given epsilon positive, we can choose n such that now you see that summation 1 over I squared, I from 1 to infinity, is a bounded convergent series. Therefore, if you start later and later, this summation will be smaller and smaller. So such that I from n to infinity of m plus 1 over I to the power 2 is less than epsilon. And the epsilon was arbitrary, thus modulus is less than every epsilon. So modulus of all path through z naught is equal to 0. And that ends the proof. Now I remember even more that the proof we gave using the Sobolev theory was pretty much similar to this. There again, we used the sequence that 1 over I is infinite, but summation of 1 over I squared, no matter where you start, this is infinite, but if you start later and later, the squares add up to as small as we wish. And this was the idea in the previous proof using Sobolev theory that we also gave. So we divided into pieces, and then the upper gradient that we found was basically 1 over I in the ith cut. So I plus 1 and so on. Okay, but again, the nice point behind this is that you can do it with different notions of modulus. It doesn't have to be exactly 2 modulus. As long as you have a uniform bound on the modulus of path joining annuli of uniform thickness. So we assume less than such thing and still get the result. So hope this has been helpful. In next video, I can actually prove this precise calculation. Until then, have a good one and thanks for watching.